Now it's fine. Yesterday there was a day dedicated mostly to software research, and today you had the chance to look at a very nice language and very nice piece of software actually. But what I want to talk about now is vice versa. It's a research software. It's actually a new thing. I mean, in IT, the research software is old. Most of IT is born from research software, but the research software as a separate problem with a separate field with a separate problems. I think it's kind of new because people are starting to understand that it is important. And as for format, let me repeat that we are going to do a lecture. It does not mention Kotlin, but I hope that after it you will understand the answer to the question that people usually ask me, why you choose Kotlin for research software. And if we still have energy after that, then we will go for a very short, like half an hour practice. My presentation has like 45 slides, but I do not think that it will be 45 minutes. It could be longer because I will get sidetracked. And please feel free to ask questions and even start unmute yourself and ask question in person. It's okay. It is cool. It's not a conference, like you can't interrupt. Please do interrupt. It's okay. So let me start with introducing myself again. My name is Alexander Nozik, and my primary work is MIPT, and I've been working in particle physics and for like more than 15 years, and most of this time I've been working on the software. So I have a lot of experience with it. And right now I'm a senior researcher at MIPT and the deputy laboratory head. And you can see this nuclear physics methods. It's not a node package manager. It's a nuclear physics methods laboratory. And I'm deputy head of it. And I'm also a team lead at JetBrains research. I do not work for JetBrains right now, at least yet. But JetBrains research, which is a separate scientific community around JetBrains. And I have a PhD in particle physics, and I teach basic physics, Kotlin, and mathematical statistics. And last year I was appointed Google developer expert, and also right now I govern the Moscow Kotlin user group. It's not huge, but it is there, and please feel free to contact me if you have any interested in making a talk on the Kotlin user group meetup, both in English and in Russian, whatever you like. So let me begin with the main question: why scientific software is different? Why it requires some kind of different approach, and how to treat it. By the way, if you have some kind of problems with the sound, please tell me. I've made a setup, it looks good, but if there are problems, please. Right. Okay. Let's start with a tale, the fairy tale as it goes, and we can call it a tale of four researchers. Once upon a time, a researcher decided to write code. And my pointer doesn't work. Okay, I just need to do a simple simulation, she said. The researcher was woman. And I will do a quick and dirty because I don't want to spend a lot of time doing this simulation, and I do not want to work with the build scripts and documentation and testing because it's a one-time thing, she said. And it will be all right, she said. And she wrote the code, and it was fine, and produced very good results. And she decided to write a paper using this code and using results from this code. And the paper was accepted into a very good journal. And after some time, because the publication always takes time, it was published, and she got a bonus at her work. And a lot of time passed, and another researcher read the paper. An interesting paper. I can use its result, he said. But first, I need the code which was used to get those results, because otherwise I can reproduce them and I can't change parameters and I can work with it. And he searched for the code, but could not find it because it was not published on the GitHub, and because the code itself was not in the paper. And he tried to repeat the code himself, and he made the code, but the results were different, and he could not understand why. And he contacted the first researcher to get the code and found that she does not work on it anymore because she ended her PhD postgraduate position and moved to the other topic. And so she's not interested to maintaining or discussing it anymore. But he was persistent, and after a few weeks of exchanging emails, he got the code, but it did not work. It was written in some strange language and relied on special environment the first researcher did, and it just failed to build properly. Not only work, it just did not build. And he asked the first researcher for help, but she was busy because she has a lot of different things to do this time, and she moved on from this project. And in the end, he just copied some code and wrote all the environment again, and it worked. But I do not understand how it works, but it does, and it produces a result, and they are very nice. And all those magical constants seems to do what I want, he said. And he decided that I will not repeat my predecessor's mistakes. I will write a library. I will insert this code inside so people do not have to think about all those constants, all those magical parameters, all those environments. I will just put it inside, and it will be like a black box, because all we need as a result. But people could use it and not spend a lot of time on setting all this environment. And after that time, the third researcher came and said, "What a nice library. It works so well. I will include it in my framework." And it uses environments, variables, it uses external files, and it has a black box of algorithm inside. And it is not possible to change that. But it could be done. So in order to work with libraries, she needed to change environment variables, especially for this part during the run, and create temporary files and a lot of things. But it could be done, and she did it. Yeah, okay, I forgot about a lot of problems, and she needed to use a very specific operation system and compiler, because otherwise libraries won't work. We can reference it in the optional chapter, the course of C++. And so like alchemy here. And in the end, she spent years doing that, and it worked. It was some kind of magic apparatus, but it did all the things she wanted. Like, it allowed you to configure parameters and put them inside this black box and get the result and get them back. But of course, in order to make the logic work, you need a proper ritual. And he wrote this ritual in the documentation that said what the phase of the moon should be, what the operation system should be, and a lot of other things. It was like several pages of documentation to make it work, but it worked, and everybody was using it, and she was happy. And then the fourth and the final researcher came, and like this one, and he found a bug in logic, several actually. But he could not fix them because those bugs were inside the black box part, and he could not understand how it worked because it was unreadable and unmodifiable. And if he tried to modify it, it will break. And he could not make the code run faster because the file IO input-output was the bottleneck, because he could not make it work without creating those files and etc. And he could not make it run in parallel because environment variables, because he has to set these global variables and change them inside in the parallel environment, and it never works. And in the end, it did not work on his computer at all because he required a different operation system to work with it and different environment, and he could not set it up. And he could not toss the code completely because all the community were using this code, and everybody were using this framework, and he could not just not use it. Yeah, plague on all your house, he said, switched to the dark side and went into consulting to get more money with much more interesting problems. It's a story of your life. You can make maybe a lot of people, older people, found a lot of similarities in their actual work with the software. You can just put pluses into the comments if you do. And this is a sad story, but it's actually very real story. I saw it a lot of times, and it usually happened this way. And this is why the scientific software ecosystem is a mess, I can tell you. What morale we have from this sad story? I will never use it again, never works in science. So the results must be reproduced. It means that even if people will not try to repeat your work, they need a way to reproduce your result. It's a great problem in machine learning, where reproducibility is very large problem, but it is actually a problem everywhere else because you also need to produce the result. This program won't need any new functionality. This also never works in scientific software because I haven't seen even one piece of code which stays the way it was designed initially. It always changes. Inputs and output formats like files and the formats needs to be flexible because they will change in future. Marginal languages, ecosystems, and tools don't stay safe because you just abandon them after some time, and the code you use should still function. Integration with the different tools should be thought in advance, because otherwise you will have problems. It won't work. Black box approach, then you wrap something inside your code and say nobody needs to understand how these things inside work. It could work in industry, in some branches of industry, but it never works in science. And do proper maintenance and think about maintainability. It's the main problem that people doing the scientific software are not thinking about it. And when I'm talking about scientific software, it's a very broad area because it includes not only the tools to work with data, not only tools to do analysis, or not only tools to do a simulation, but much wider variety, including, for example, software to acquire data from your hardware. If we talk about experimental science, both physics and biology or whatever, we are talking about control software, where you want to control systems, change some parameters, data storage systems, web services. There are a lot of things that modern researcher needs to work with. So in the end, the problems we're talking about are the same as for industrial software. I mean, for things like databases and other things. But as you saw it, there are much more problems with the scientific software because the programmer's qualification is low in general. I can say that I won't say that any specific developer in science is less qualified than a developer in industry. But in general, in science, people are first and foremost know their target field, I mean physics or biology, and the programming expertise comes secondary. Longer support times. They say it in industry, you need to think ahead because it will live for a lot of time, but a lot of time is different in industry and in science. In industry, you can say that 5 years for software is a very long age. So that you can safely rewrite the software after 5 years. But in science, for example, you create an accelerator and it will function for at least 10 years, more like 20, and you can change the data readout system mid-run. So you need to think in advance. I'll finish the slide and then answer the question. Short employment terms, it's also a problem because in science there is some processes like PhD students going away, postdoc positions ending, etc., etc. A lot of migration of people inside science. So it's a very common thing that someone started to work on the project, spent like 3 years or 4 years on it, defended his or her PhD, or ended his or her postdoc position and made an article or paper or several ones, and then went to completely different thing and to never work again with the software he or she developed. Also, more diverse ecosystems. So scientists want to try different things and they try new languages, they try new technologies. This is what is science is for. But in the end, it is also a problem because those tools not always work together. Science is, or at least should be, open source. It means that you will have a much larger development community. So a lot of people with different backgrounds will work on the same project and with different level of expertise for a long time. And of course, it's a good thing, but it is also a problem that scientists in general are very artistic. So it is good because they invent new things, and it is bad because those things are not always well tested and well maintained. So now for the question, don't use marginal tools or ecosystem. That new tools start small and then grow. And if the idea is that they should be used only when they got adoption, no, it's not the idea. But of course, you should always try something new. This is what science is about. But the problem is if you're using some kind of very specific tool or language or whatever in a scientific project, and then different people want to use it, they usually can't. So you either should use more or less established ecosystem. I do not mean tool, I mean ecosystem, or you should think in advance about integration, because you need to always think how your code will be used and how will be integrated with other code. We know a lot of problems when people do not think about it in advance. So I stated the problem, so that the scientific software requires all those knows all those problems of industrial software, but maybe those problems should be multiplied by 4. And let us check some things that usually are sore points and see if we can at least try to develop guidelines how to make it better, how not to make the same mistakes people are doing. Architecture, it's the main point, because it is very hard to learn to do proper architecture. There are no guidelines, or there are no guidelines even in industry. There are some patterns like clean architecture or similar things, but they do not always work with a complex software. And so there is no general recipe how to do it better. And the only way to learn doing proper architecture is having a lot of experience with it. But let us try to see at least something, some ideas how to make it better. Here's the example, and it's an example from the framework which is widely used in particle physics. It's a CERN root developed by CERN. Yes, we are discussing the challenges of researchers in software engineering, and we'll try to invent a way to solve them. So CERN root, I will make a lot of examples from it, because while adopted from the engineering point of view, from programming point of view, it is very bad. So not that the code is bad. There are pieces of bad code and good code, but the design violates all the principles of good software. So there are a lot of problems, and this is exactly the case I stated in this tail forward, because everybody is using it, and you can't avoid using it. But it is a pain. So here you see a part of documentation of histogram class. Histogram, you probably know what histogram is. It's just the number of beans with a number of counts for each bean. And you see, just from the documentation, you see that there are a lot of things this class does. It includes labeling axis, which is not relevant to histogram. It's relevant to histogram representation. It includes information about binning, which is about filling the histogram. It includes information, a lot of different methods of filling and manipulating histograms, drawing histograms, making analysis on histogram, and putting it all into a file. And everything is inside one single class. It is a problem. So let me see if I listed it all. And it's a problem. Why? Consider that I want to change a container storage logic. For example, I want to use not array of beans, but instead I want to use a map dictionary in Python, or I want to use a tree map in Java or Kotlin, which tree map is could be better because it allows you fast search between beans. Or I want to use any other implementation, for example, rely on external library. I can do that because all those behaviors are tightly coupled. They are working together, and when you change something, everything else is broken. Consider I want to change the serialization logic. For example, I do not want to use default serialization used by CERN root, which is actually a binary, self-made binary format, working not unlike Java serialization. But if you know what I'm talking about, Java serialization uses runtime information to generate serialization logic, and CERN root parses the source files to find out this information, the information about serialization schema. It will never work. So in order to make XML or JSON, you need to change the logic. Again, you need to change something that will break a lot of code. I want to use different kind of visualization. It completely fails because right now the visualization is a part of the class itself. It visualizes itself. So if you want to use a different engine like Plotly or any other web tool, you will have to change all the logic inside this class. And as I already said, if you want to use complete external histogram taken from, I don't know, remote storage or whatever, you can do it as well. This is things why people teach software engineers nowadays not to use tight coupling inside logic. And it happens every time because people think that if I'm creating a class, I need to add a functionality to it. So they adding everything to it. You should not do that. And here is the how it works. By the way, there was a question about slides. I will share with them after the presentation. There was how does it work from the inheritance point of view. When we start talking about C++ or any other things, you usually hear, okay, we are learning object-oriented programming. And what does object-oriented programming mean? Object-oriented means you have a lot of classes, a lot of inheritance, and you can just put it together and it should work because it's wholly object-oriented programming. And here we see the case where what I could call an object-oriented abuse, because inheritance is not used properly here. You see, for example, that th3, which is a three-dimensional histogram, inherits one-dimensional histogram, but they do not have things in common. They have a different kinds of bins. It means that three-dimensional histogram will have some behaviors which are not intrinsic to three-dimensional histograms. And there are a lot of other things too. For example, things like they are done specifically for visualization, only inherit the logic of a histogram, which also does filling, serialization, etc. It is a problem. Let's see why people use inheritance. They write a code in the ancestor to use it in its children. Say, have you done it even once in your life? You can again write it in comments. While you're writing it, I can say that it's a bad practice because this is not why inheritance is made. So it's not to add the functionality to a class. A lot of examples where it fails. Include behaviors from other classes. Again, it's not what object-oriented programming is done for. You probably know words that composition is better than inheritance, and this is exactly the application point. To isolate protected members, I mean, forbid access to some internal fields to external users and use it only in the behaviors you want. Well, it's okay, but in my practice, it usually also could be avoided in public classes, because if you have to hide something, you probably not organize it well. Provide abstraction to separate declaration and implementation. Yeah, this is exactly what is object-oriented programming is for. And this means that usually you provide an abstraction and then you provide implementation. You do not do it like this way. You do not do a lot of levels of inheritance. And if you have like 5 levels of inheritance, probably you've done something wrong. Also, there is a thing that is not available in classic C++, which is a dynamic dispatch for silhouette exhaustive hierarchies. Anton showed you an example of such things today at the morning. And this thing is actually a very good use for inheritance when you have trees, inheritance trees, for example, for events. You have different kind of events, and you use in Kotlin, it's a when case, when container, and switch over different types of events. But these things is okay in Kotlin and in Java, but it does not work in C++ because you can't dispatch events based on this on their type. You do not have access to C++ types in runtime without additional work. Why I'm talking about C++ a lot? Because most of scientific ecosystem right now in C++, and it's a huge problem from my point of view. Okay, what we want from a good hierarchy, we want you not to abuse abstractions if you don't need them. So don't create intermediate abstraction layers if they're not used anywhere, just for the sake of it. Don't use inheritance to provide additional functionality to existing classes. And here, where good language actually helps you a lot. Again, you saw the examples in Kotlin. In C++ and even in Java, if the class does not have a functionality you want, what you would usually do, you create a subclass and add this functionality. But from the architectural point of view, it is a very bad thing. And you should add composition wherever you can. One trick, again, it's common for industrial development, but researchers usually do not understand it, that you should design the interfaces and first see how those interfaces interact, not implementation, but interfaces. In C++, it will be virtual classes. In Kotlin or Java, it will be interfaces. And again, I said that multi-step inheritance without good motivation is a bad thing, because you will get confused in the future. It will just confuse your logic without adding anything. Usually there are 2 or 3 levels of inheritance, like interface, abstract class, if you have several descendants, and implementation class, and that's okay. So not quite easy to understand, but as I said, architecture is very hard to grasp because it requires experience to do it properly. You need to understand what could go wrong, and for that you need to think in advance about what could go wrong. Prototyping, and to understand what could go wrong, you need to do prototyping. And why is that? Why is that? Because your code will change several times. The code that never is written from scratch is bad by default, I think. You just can't create a good code from the first time, whatever you do. Your architecture will change, because during writing this code, you will understand that things you thought would work won't work. And this means that the whole layout of your program will change in the future. Your implementation will change, of course, and if you designed it good, your architecture doesn't depend on your implementation, but it is not always possible to do that, even if you have a lot of experience. And actually, the problem you solve will change, and I think a lot of you encountered this in your practice when you're starting to work on one problem, and after some time understand that the problem is completely different. You need to solve different problem. You need to work with different kind of data. You need different ways of analyzing it, and you need to provide results in a different format. So the prototyping is inevitable, and I think it is a good practice to always make time for a prototype. Nowadays, if we are doing a commercial job for some company, we are doing exactly that. We are saying the first stage will be a prototype because we need to understand how all things work. And only at the second stage, we will start writing the code for the final application. I do think that making everything work from the start is not a good idea. The second thing, and here we have a lot of new things in the software engineering last several years, is a modularization. I mean, now we have a new understanding and new tools to provide, to separate our code into different modules and different parts. Of course, if we are not talking about C++, because in C++ modularization is very hard to do. So we have two different types of architecture we can work with, and they are not those terms here are used not very strictly, but in more broad way. So the first one is a monolith. It's not about here. It's not about the runtime architecture, but about development architecture. I mean, how it looks when we are developing the code. In case of monolith, all framework components are developed together as a part of a single code base. In case of something I call services here, all components are developed separately in separate modules or even in separate projects, and in some cases in separate languages. The monolith approach says that if you have a separate modules, that all versions should align. You probably encountered that as well. So in order to use the software of the module of given version, you need to also use the proper version of the framework. Otherwise, it won't work. Because, of course, we now have a semantic versioning and we try to do the backward compatibility. But again, in the complex code, it never works perfectly. The code base, I mean the whole code for the project. Yeah, actually it's not a bad question, because I do not clarify this term because it's probably obvious for experienced developer, and it's obvious for open source developer, but there could be different meanings of the code base. And here I mean the whole code for your project. Again, maybe I should point it again that we are talking about software development. We are not talking about using the software. So the final user of your framework do not have to know about your code. He or she just needs an instruction how to install it and run it. But I'm talking about the problems of the development, not about the usage. And it's a very important difference. Thank you for questions. In the service approach, versions are not aligned, but you have aligned APIs. I mean, different components need to know how to call each other. It could be web APIs when you call it with a JSON or a REST call, or there could be clearly defined API boundaries inside the program itself. So when part of your program is known to have these functions with those signatures. In Kotlin, they now have even tools to validate those public APIs. So when you change something, you will have an error during compilation if this public API is changed. In monolith architecture, it's not very important how parts inside the program communicate, because when you change something, at least if you're using proper testing framework, proper continuous integration, it will always work. And you do a refactoring, for example, and it changes how the functions looks in the whole program. So you do not think about how different parts of the program operate with each other until it works. In services, it's not that easy, because if something changes in one part, you can guarantee that the same thing changes in the other part. So you need to rely on message specifications or APIs, again, API description, to make it all together. From the looks of it, it looks like monolith is much easier, because save for the version thing, services require a lot more work to implement and to maintain, and it is truth. Monolith is much easier to develop because you can always change things inside, and the user of this product could not see what's happening, and it's okay. You just change things to make them better. You can introduce features much faster. I hope you understand what I mean by features. Here I mean not commercial features, but the features of your analysis system or data system or control system. You have more control over development process because you can see the whole project at once, and you can, if you see a problem, or for example a bottleneck, for example you have a performance bottleneck somewhere inside, you can localize it and immediately change everything to make it better. But the thing is that monolithic architecture is much harder to support. Why? Because consider this thing: you have several people working on this monolith, and one guy is responsible for the whole project, like tens of thousands lines of codes, or even hundreds of thousands of lines of code, and then there are tens of other people working, and each one of them need to understand the whole system before they can do proper changes to it. And you can't say you guys are working on the one part of the system and never see other parts of the system, because they all interconnected. Also, you should remember that in science, the terms of employment are shorter, which means that if one guy developed a very good project and then went away for different work, for different postdoc position, new guy, the new one who will be developing it further, he or she needs to fully research the whole project, fully understand each of its parts in order to make it work. It usually takes years. So it's a common thing if you come to the new project, new system in science, for example, control system. We're now working with Duke's control systems in DAISY, and you need to spend at least half a year for experienced developer and like years for inexperienced developer to understand all features of this thing, to make it work, to make it build, to understand how to make changes to it. So after some time, like 5 years, it's very hard to find where something happens. And as I said, it does not work well with separate development teams working in parallel. So it is possible to make it work, but you need to enforce very strict rules on the code quality, on commits, on API boundaries, etc. And then scientific community, as I said, they are artists, we are artists, and do not work well with the strict rules. So this is why a service approach is much more popular in a lot of fields in the industrial development. For service, you require more manpower to begin with, to create the initial architecture, and it's much more sensitive to design error. So if you error in monolith, you will just refactor and fix that. If you make a error in the service development design, then you will need to wait for a new version to yeah, where we are artists, we are more sense. Then you will have to wait for a new version to fix this error, because you need to break this API to do that. But on the other hand, you will have much easier maintaining costs in the long run. This API infrastructure of communication means that you can make the development in parallel, so different groups can they do not have to explain the whole code base to each other. They need to explain only, I need this kind of data with these flags to be sent to me, and my code will work. And it's much easier to test it, to write tests that test each part of your code separately. It is easier to replace implementation. It is very important because consider this thing that your system is working, but you decide that the part of it is working badly, and you need completely different approach to implementation. And unless you change the API, and if you design it well, you don't have to, you just switch to new implementation, and you can even maintain both implementation at the same time. So you can interchange them. It's very important because you can compare them. You can compare. You do not have to immediately refactor the whole project to make changes to one of its parts. And additional thing that it is easier to adhere to add new functionality unless it changes the APIs. So you can just add new types of messages, new types of APIs, and it will go smoothly without changing anything else in the project. Right now, Kotlin adopts a very interesting approach in Kotlin itself as a language in the standard library. They have a very interesting approach into this deprecation cycle. I mean, they introduce new features, and then the old features still working, and after some time they got this warning that you should not use it because it is outdated, and after some time it generates error. It's very good for maintenance, a very interesting practice. Yeah, what to choose? What to choose, monolith or the service architecture? In general, again, I said it's very, very broad terms. There are a lot of shades of gray between them. And the correct answer I should answer, the correct answer from me is you are the cowboy, you should jump. I don't know if there is the same joke in English, so I took a picture in Russian, and it's an old joke. Then the cowboy is galloping, and he sees like a hole in the ground, and he says, I'm a cowboy, I will jump. And after some time, and he jumps, and after some time, the hole is very large, and the horse tells him, you're a cowboy, you should jump. So in general, you should decide, because it depends on your problem and your specifics. But my answer, which is not very politically correct, is that you should use monolith if you have a tight team, very fixed team, and you do not expect the project you are working with to spread beyond your team and the lifetime. If you do not expect this project to live for a long time, for example, if you're developing a control system software, no, it will definitely should live for tens of years. So it's not the case. And if you are going to make it for a time, to maintain it for a time, it's like a data analysis framework or simulation framework or a control software. It's much better to think in advance and spend some time designing it, and then use a highly modular approach to use. Of course, again, as I said, not all ecosystems provide the same level of modularization support. Java and Kotlin are very good in this regard. Student term projects are usually monolith. Yes, of course, exactly because of that. Because you need to make it fast and you need to produce the results. But the problem, if you want to make it beyond the student project phase, you need to rewrite it completely, introduce new architecture, because we know a lot of examples where people start with this very small, very good working code, and they say, and then they try to use their code outside, and it's going to hell from there. Is there some sense to try and combine approaches that is use servers for some aspects and not others? Yes, indeed. You always should decide what is better for you, but you need to remember some things. You need to remember that the points I said earlier, that your project will be used not by you, but by other people. You need to think in advance how your work will be used. Okay, here is actually what answer to Johan. A compromise, it's API boundaries. The term I invented just for this talk, I have not encountered everywhere, but it's obvious concept. So you do not have to create a separate services, I mean separate web services, but you can create a very clear API boundaries inside your code. So you can say that nobody should use APIs, any API, but those which are allowed. If the code uses APIs which are not in this API boundary rules, it should not be used. It helps a lot. Again, in Kotlin, it's solved by splitting your project in separate modules and putting all those non-public APIs with a modifier internal. It means that nobody outside this module could use this API, could call this function, and it works fine. Sometimes it's frustrating because you encounter a function you want to use, but it's internal, and yeah, it is. But in the end, it helps you a lot because the one who put this function there did not intend it to be used externally. It means he or she can change it without notice. Code quality. Code quality is an important thing. And in order to maintain good quality, you should remember several points that you are not the one who will be using your code. It's not always the truth for industrial research, because it could be closed source and it could be application for final user. But in research, in scientific software, it's almost always the case. So you're not the one who will be using your code. So code must be documented, others will read it. And there is some kind of cult of self-documenting code. They believe that if the names in the code are written properly, then you do not need to write the documentation. Never works. Never works. It works for you. It could work for you in a short term. You will understand what you have written. But the other guy, he have a different understanding on naming. So without at least small amount of documentation, it never works. And code must be tested. This thing is now widely accepted in the scientific community. So people use code coverage as a criterion of quality, but it's not always the case. So the coverage could be good, but test could be bad. At least you should test the primary functionality and not obvious parts. And of course, it depends on the ecosystem and language you're using. You need very large code coverage for ecosystems like Python, JavaScript, or Julia. And the amount of code coverage in Kotlin or Java or in most strict languages is not that, the requirement is not that high. The build process should be automated. It's one of the main sore points in using modern software. I was reviewing a paper recently, I mean, in Journal of Open Source Software, and yeah, I failed to build it. They explained that they gave a long, like 2 pages of installation manual, but I did not make it work because my environment was different. And they said that they need this specific environment for this to work. It's a very common case. So the build process at least should be automated. I think it should also be available from different platforms, but it's too much to ask. APIs and API boundaries should be clearly defined in the documentation. Otherwise, there will be a mess because people will try to use some internal functionality of your code and they will be unhappy when it breaks in the new release. You will be very you will the more you restrict in the beginning, I mean from usage, the more freedom it will give you later to improve things. If people want to say there is a, I think there is a principle in the software engineering that you should forbid everything first and then allow later if people ask for it. Okay, if you're not convinced, try to read this random piece of code. It's took from Gian4. It's a primary framework used for simulation and particle physics. I haven't selected the most unreadable ones. It's just a random piece. About Dockerizing, it's a very good question, and I say no. Docker is some kind of crutch. Docker will help you. Docker will gives you illusion of maintainability, because Docker is made for the end users. So for the end user, it's much easier to create to just up the Docker container and run it. But if we are talking about development, not about usage, Docker will hinder you, because again, you're just saying that you still need to set the development environment correctly. And yeah, the end user could use it, but the other developer will spend a lot of time trying to replicate your build. So I think for development process, Docker does more bad things than it does good things. For the end user, yeah, it's fine, it's okay, and it's a common practice. Unless, of course, you are doing microservices. In this case, of course, you can Dockerize everything, because you do not expect other people to interact with your code at all. You provide it as a web service. No, because Dockerfile allows you to run software, but not develop software. So you need to set up all your build environment, all your debug environment inside Docker. Otherwise, it's not that easy. Again, I can't say that Docker is bad. I mean, it generates some bad practices, like we do not care about the build process, we will put it in Docker. It's not good, because it will cost you a lot during the development process. Documentation, yeah, it's already said that the self-documented code is a myth and it never works in real life. And here is the example of good no, again, Domenico, it's a different thing. The shared pipeline will eliminate the problem of build reproducibility. I mean, you will other people could may run tests, but when you do actual development, you do not need to run tests. You need to load your project into IDE and work with it. It's a different thing. It will build in the CI, but you will have a lot of problems of running the development process itself and running tests, running debug. Yeah, it's not obvious. It's not an obvious thing, but you need to think about these things in advance. Otherwise, you will have a lot of pain working with the other people. I've seen it multiple times. For documentation, you can see this is one of JetBrains products. Sadly, documentation is not very good in all JetBrains products. So I selected the one with a very good ratio of documentation and code. You see down here, it's like 100,000 lines of code. Of those are 20,000 lines of comments, and it is a good ratio. So it's like a quarter of code. It's not possible always to document everything, but at least public APIs and main methods should be documented. Testing, yeah, I'm not sure if you're old enough to remember this. This one. But one more test, and the testing is very nice, and testing is very good, and testing you should always do. In Python ecosystem, you can't work with this. If your Python code doesn't have tests, it will be garbage in a month. Julia less that, but still needs a lot of tests. And Kotlin or Java, you need smaller amount of tests, because a lot of things are tested automatically by type system. But still, tests are important, and code coverage does not always mean that you have a good test suite. Yeah. Build again, as said, it's a picture from a Gradle site, and there are different ways of doing build. Of course, it does not mean that you should always do it. You can do a manual build by setting a bash script in the root of your project. Never do that. It's unmaintainable. Even if it people could say that it's the most flexible way of doing things. Yes, it is, but it's not maintainable way of doing things, because nobody will be able to replicate or even understand what your bash script does. I could say that you should not use make in a large project as well, because in make, again, it's a huge, it could be hundreds lines of code. Nobody will be able to understand that. Make does not play well with the modularization and other things. So if you are unlucky and you have to work with C++, use CMake or Meson. Meson maybe not the best idea, at least from my experience, but you can still try. Auto tools are outdated. In Java Kotlin ecosystem, the build tooling is very good. Maven and Gradle are great pieces of software, especially Gradle. But again, you need to spend time researching and learning your build system, because build is important, and you need to know how it works. Even it is hard, even it is not unpleasant. I mean, the build tool, I'm not sure. In Python, people usually do not use a build tool at all. They just create this distribution for PyPy or whatever. I don't like it. And there's a huge problem with Python with the reproducibility of environments. And people from Facebook even tried to introduce Gradle support for Python, but it never worked. In general, I think my recommendation is not to do large projects in Python at all. One of the main problems is lack of build tooling. So Python is good for initial prototyping, because you do not have to think about the build process. But if you want to create a maintainable software, you need to think about build tool as well. And of course, different languages also have different tools to build themselves, like Cargo in Rust, Webpack in Julia. It's inbuilt system, but of course it all depends on what flexibility do you need in the end. Yeah, you do not, an important thing to remember about build process, like things you should just say in your mind where you're doing the build. The build process is not that you can build the software later. The build process is done so the other guy will do it later. And this guy is not necessarily familiar with the ecosystem and proficient enough. Build is not only for building, which is a controversial point. We can discuss it later, but actually build is also about deployment, testing, documentation, and a lot of other things which you need to do to make proper software. I'm a little bit out of my pace. So data forms and protocols, it's not a general problem in the software engineering, but in science it's very important, because again, different pieces of scientific software will interact with each other, and for that they will have to understand it. And for example, the CERN root serialization format, which again the standard in the particle physics, is a real pain, because you can't read this format outside of this C++ code. Nobody else can read it properly. They are similar problems with the common formats like HDF5, because HDF5 is a huge format, like hundreds of pages of documentation, and the only one full implementation is in C, very low level, and the only one high level implementation is in Python. So yeah, it's documented contrary to the third route, but you can't create new implementation of this format. So the truth of life that each researcher working with data invented a new format at least once in his or her life. I invented several, but the motivation is different. Usually they take about faster execution, sometimes about better compression, didn't know better, didn't know that there are different formats, and just because they could. That's also motivation, but it never works. In the end, it won't be faster because industrial standards are very fast, and you can't expect you will do it better. It probably won't be more compact because tests show that compressed JSON is very compact. If you just zip JSON, I will get to the examples, but for example, it's again a serialization format like or some data you're getting from device, like binary representation. Like I have my spectrum as a pairs of two numbers, one a channel, one is amplitude, and I pack them in a self-made, homemade binary format. This homemade protocol must be thoroughly documented, and even if it is documented, the documentation is never full. I've worked with several hardware homemade protocols, and in a lot of cases it is documented, but then they change something and then have not changed the documentation. So again, nobody but their software could read this format. Of course, if you want a proprietary software, so nobody but you can work with a file format, it's okay, but it's very bad for maintainability and the future of your project in the science. Yeah. Very short introduction. I can give a separate lecture about schema-based and schema-less formats, but in general, you should see about existing formats. For schema-based formats, schema-based means that you know the layout of the data, like it's two numbers or three numbers, a vector or three numbers, and some sub fields. You should probably use something like Google protocols, which are fine and have a implementation in all possible languages, like protobufers, flat buffers. There are also formats I have not tried, like Avro or Thrift, but at least they have implementation in different languages. In most cases, you probably will want to work with the schema-less formats when you do not know the layout of data in advance. It's less effective, slightly less effective, but much more human readable, at least if we're talking about JSON. And JSON is actually almost a good choice in all cases because it has very good parsers from web industry. It's implemented in all languages. It's human readable, which is important for debug purposes. And if you compress it with the zip, for example, it's very compact. Actually, it's much more compact than the binary format. The only problem is that the compressed JSON could have some performance issues when you parse numbers. Parsing numbers from string is an expensive operation. But otherwise, if you do not have those constraints, just use JSON, and then you can add any more effective format later. Okay, I will probably skip that unless you ask, because in serialization, there is also a problem of dumping Good question. XML is basically a schemaless format. So you know what XML is, but there is a developed thing like XML schema, and it allows you, there are a lot of tools to work with the schematized XML and validate it and do all things you can do with these formats like automatic serialization, etc. There are things for, yeah, I mean, for example, SOAP, but there are a lot of other tools, not only SOAP. There are JSON schemas as well, but they are not that thoroughly developed as XML schemas. And of course, if you inside, for example, a single ecosystem like Kotlin, you can create data binding. I mean, use your classes as a schema for your serialization, but it doesn't work well outside of your ecosystem. Okay. Data testing and reproducibility. Oh, this is very important, and it's a picture somewhere from the internet. And again, research must be reproducible, otherwise it does not work it, because what one researcher did, the second one need to repeat. And two different researchers should have the same result with the same assumptions. It never works this way, because there are always differences. If two researchers write a more or less complicated code, even completely the same assumptions, completely the same data, that the result will be at least slightly different. And it means that, and the result should not change from version to version. It could happen, oops. And the result should not change in different environment. Those two requirements we can meet. The first one, never. So in order to do all that, there is a special kind of tests you need to add to your scientific project. It's a data test. You know that a unit test, but the data test is some kind of integration testing when you run the whole pipeline, the whole your process against some reference data. And then you compare it to some reference results. And of course, you need to introduce some kind of margin of error here, statistical or whatever, and not exactly coincidence, but with a margin of error. It allows you to change things in your code, change how things, test different algorithms. For example, from version to version, you change the algorithm and you expect it to work faster, but with the same result. In order to test that, you need this automatic data testing to see if it does not break anything. It's a huge problem in, at least in particle physics community. Then results of the simulations change from version to version without any notice. It's a really problematic. So I think any code that works with data or produces some kind of data-like results should have those tests today. Legend ecosystem. I specifically dedicated not a lot of time for this topic because, you know, programmers could talk about languages for weeks and months, and probably obvious what language I do prefer. And I won't say that it's the best language. I believe it, but I won't say it. And I wrote an article about this. You can use a QR code on Medium and check it. And there are some takeouts from this article. It's a first statement: the good programmer could write a good program in any language or ecosystem. Ecosystem is much more important than language. A good language is a language. The good programmer will write his good program. I mean that it is not important that language is good. It is important that it is convenient for developer to use it. And this is important. So, and the second statement, yeah, it's also very important. And a good language is also a language which not so good programmer will still write a good program. And this is much harder because you can find a genius who is writing the perfect C++ code. I never saw the guy, but probably they exist. But the problem is, again, we're returning. You are not the one who will be using and developing your code. If you create a code in perfect C++, the next guy who will be developing will know almost nothing about C++ and will make a mess. And we have to work with this mess right now. And there's also a question of price, because, for example, in Scala ecosystem and C++ ecosystems, the developers that could do good programs in C++ and Scala are very expensive, or in Haskell, for example. They're very expensive. It means that you can't allow to hire them on your scientific salaries. It means that you will have to think about the maintainability, again, the maintainability of your code. So if this is the language only you know, then it will never develop because you can never hire. TDD, what do you mean by TDD? If you can expand the abbreviation. Test-driven development, I think, yeah. Yeah. No, it could be, but I do not think it will work because you never know in advance what you will get. Again, it's artistry. It's a piece of art. Any scientific program is a piece of art, more or less. So in order to write test-driven development, you need to know exactly how it works in the end. But in science, you never know how it will work. The data test is a kind of test-driven development, but not for unit tests, but for integration tests. And for the whole data, you usually know what to expect. At least you know what you get from the first version, and you expect the second version to produce the same result. Or you need to explain it in documentation why it has changed. Performance is a myth. This is very important thing, and maybe we will have a discussion about it, because yeah, very good question from Shamsa, if I correctly pronouncing your name. It's a very good question. Please, I will return to it in the end, and we will have a separate small discussion about it. Okay. Performance is a myth. It's my statement, but in my career, I found its statement true. Why it is, I will explain why it is. There are different types of levels of performance. There is an algorithm complexity. I mean, if you use a squared algorithm, n squared algorithm instead of n algorithm, it will be slower. There is a bottleneck in numeric operation, CPU intensive operation, or your IO intensive operation. And there is a result catching and memoization. It's optimization of not of algorithm, but of a reuse of the algorithm with the same parameter. Caching is not about the algorithm itself, but about multiple calls of the same algorithm. And from that, algorithm complexity does not depend on the language. So you can write a correct algorithm in any language. Those things like bottlenecks in CPU or IO are usually solved with low-level libraries written, for example, in C, and we can have a NumPy as an example. So the Python is very slow, but if you write all performance critical operation in NumPy, it will be pretty fast. And this one actually depends on the ecosystem. And depends on tools, because if you have convenient tools to do caching, to do proper architecture, to do proper communication, to cache the results, you can save time. And you see that in this case, not the fastest language wins, the more convenient one wins. And again, I've saw it multiple times, and there are people who are saying that the program is fast just because it is written in C++, and then I write it in Java, and it starts working like 20 times faster because I have better tools to profile performance. I have better tools to find these bottlenecks, and I have much more convenient data structures for data structures, and they're optimized for performance. Could it be a good idea to use C instead of C++ in low-level programming certificate? Probably not. If you are allowed to use, again, the bottleneck is usually in some kind of code which calls already optimized libraries like BLAS or LAPACK or any other, or TensorFlow. And if you're allowed to call those libraries, it doesn't matter which language do you use. Actually, our benchmarks show that Java performance for most operation is the same, at least the same level as C or C++ or Rust. There are difference like 2 times in both ways, and it's not important because it's micro benchmark. When you go for a larger program, the convenience and the optimization of not this bottleneck optimization, but global optimization is much more important. So this is why I say the performance is a lie. Performance is a myth, because not because it's not important, but because you can get good performance on any language if you want. And you do not need to decide on ecosystem and language because it's more performant. And as I said, a lot of physicists write the code in C++ because they believe that C++ is faster, but they never measure it. I don't remember if I wrote it here. Probably not. But if you are not measuring performance, you can say that it's fast. Just today, I had a discussion with a guy writing in Go language, and he said, it's close to the hardware, so it should be fast. I said, have you measured it? No. If you haven't measured it, then you can say that's fast. And there are a lot of ways to make a slow code on the systems language like C, C++, or even Go. And you need to understand that not only code execution takes time, the development time includes compilation time. For example, for C++ or Scala, it is important. There is maintenance time and maintenance people availability. And this goes, for example, for Python. You can write a very fast and very nice program in Python, but if you do not spend time writing tests and documentation for this program, you will have a very long maintenance time. So it's hard.